Good day. I cordially welcome on behalf of NTI Audio. Maybe you have participated in our last webinar on basic sound level calculations, and subsequently we received a couple of questions and suggestions from your side, which led us set up another webinar on more sound level calculations. But first, I want to squeeze in a short side note because today, we are celebrating the 50th webinar at NTI Audio. Thanks to your loyalty, thanks to your interest and your feedback during these years, we were able to set up all these presentations and to supply you with the requested information. That makes us very happy and proud. So thank you to you from our side. My name is Markus Becker and I'm presenting this webinar today, and I'm assisted by Greg Schmiedle, our product manager. He is taking care of the incoming questions and comments. On the left-hand side, you see the topics that we have prepared for today. It starts with the subtraction of sound levels. We will say some words about the measurement accuracy, as well as on the relationship between sound level and distance. At the end, we will also introduce you to the noise exposition level and how this can be calculated. You see, green shaded means that we will have practical presentations for these topics as well. Well, the presentation will last a little bit less than half an hour. Let us start with the subtraction of sound levels. And actually, we have two typical applications or two typical views, and I'm going to start with the first one. Let us assume you are in a machinery hall and you are requested to measure the sound level in that hall. You measure the 85 dB, and now the owner asks you, well, if we switch off this machine here to the left, can you determine the sound that is coming from this specific machine? So we switch it off, you remeasure because the other machines are still working, still producing their noise, and we are coming to the 78 dB in our second round of measurements. And now the question is, with these two values, can you determine the amount of noise that is coming from this specific machine? The answer is yes. All you need is to enter the corresponding values into this formula. Here to the left-hand side, we see the target, the level of this machine. And here on the right-hand side, we have to enter the total level of the noise in this machine hall with all machines running, and the level in the hall with this one machine being switched off. So the level without that machine. And when we enter these values and calculate the corresponding results, we will receive the noise that is originating from the specific machine. If I'm giving you an example with these two values that I have just mentioned, the 85 and the 78 dB, we will find out that the machine itself is contributing with a level of 84 dB. But as I said, we can also take a look at this topic of subtracting sound levels from a different view. And this is what I'm showing here. Here we have an array of loudspeakers, and these loudspeakers are creating a certain sound level. So you establish a measurement, you set up your microphone, and let's assume you're measuring an average level of 85 dB. Now, the question is, what will happen if we switch off or if we remove one of these loudspeakers? And let us assume you know that the sound level of this specific speaker here in the corresponding distance would be 78 dB. So you know the overall sound level when all loudspeakers are active, and you know the one from this specific loudspeaker. Well, can we determine with these two values the new LEQ of this array without that speaker? The answer is yes. And actually, it's the same formula as the one before. We enter the total sound level from the beginning with all speakers being active. And then we just subtract this term here where the level of this specific speaker is part of. And then this way we can calculate the new overall sound level at this position, even without measuring. So as an example, same values as before, 85 dB overall level, 78 dB from the specific loudspeaker, and we're ending up with the 84 dB. But let me show you that in a practical example. Here we have, in my setup, I have two talk boxes. The one talk box is representing the kind of background noise, the fundamental ongoing noise, and the other one is representing this single source that I can switch on and off. I'm measuring with a microphone that is positioned in between these two sound sources with an XL2, and you can see this green content of my XL2 on my PC. And by the way, the levels of these talk boxes are generated from this FX100. But let's take a look at this setup. So I switch over to the FX control software and the screen content of my XL2. So the first step is just to verify the level of the first talk box. You see it's 78 dB. And now I'm going to switch on both talk boxes, which should end up in 85 dB. And after a couple of seconds, I will switch off here the upper talk box, and then you will see the result, the difference that will appear as soon as this part is muted. So you saw, as predicted, the combined sound level is 85 dB, and as soon as I remove the upper talk box, the remaining level is 84 dB, exactly as I showed you on my slide. So let's step over to the next topic, and that is a completely different challenge. Here you see a band playing music on the street, and maybe the neighbor complains that it's too loud, and it asks you, can you measure the sound level coming from this band, and just to find out whether it's beyond the allowed limit or not. Well, of course, you can execute a measurement, but as you see, behind we have a street scenery, we have maybe cars or motorcycles driving by, creating noise. So how sure can you be that your measurement actually represents the level of this band? So how can you ensure the accuracy of your measurement? Especially when we have to consider that there is an environmental noise. You can also turn that question around. How loud may the environmental, the background noise be to still allow an accurate measurement? Well, the answer is hidden in this graph here. What does it show? Let's first take a look on the x-axis. Here we have the signal to noise ratio, which means we measure the total level, which is the level of the band playing plus the background noise. Of course, we will do that over a couple of seconds to get a decent average. And then we wait for a pause where the band is not playing, and then we measure the background only. And when we subtract these two levels expressed in dB, we get here the corresponding value on our x-axis. Now, if we, for instance, have the demand to execute a measurement with an accuracy of minimum 0.2 dB accuracy, which means that the error the deviation of the reality from our measurement value is not larger than 0.2 dB. Then we could, for instance, draw this line here from the 0.2 over to cut the green curve, and then we see we would need a minimum signal-to-noise ratio of 13.5 or maybe better 14 dB to be on the safe side. So this is the way how you have to interpret this graph. Of course, you could also do it the other way around. Let's assume you determine the signal-to-noise ratio and it is only 6 dB. In that case, you know that your measurement result will be maximum 1 dB close to the reality, or let's say, no, I have to say the other way around, that the maximum deviation of the reality from your measurement can be 1 dB plus minus 1 dB. So this is the way how you interpret this curve, and this is the way how you can determine how accurate your measurement actually is. Coming to the next topic, the relationship between sound level and distance. Well, the challenge here is you want to purchase an apartment up here in this building, and you want to know how much noise will you have to expect from these trains passing by. So you know up here, this is where you are interested in measuring the noise, but unfortunately right now you cannot go into that apartment. So you have to do it in an indirect way. What you can do is you first measure the sound level here at this point from the train passing by, and then by knowing the distance to the train and by knowing the distance from the train to the apartment, you can determine the expected noise level up here. And the formula to do that is here, shown here. It's quite simple. All you need is the sound level, the measured sound level at the first position, the blue dot. You need the distance from that position to the train, and you need the distance from the target position to the train. And if we enter just as an example, here 72.7 dB, that's your measurement result from that position. We know that it is 25 meters away from the train, and we know that the apartment is 100 meters away from that train, railroad. In that case, we could expect that the train-induced level up there at the apartment is 61 dB. And this is also something I want to show you in a practical example. For that purpose, I have just one talk box. I'm using one talk box with the XL2 sound level meter and the microphone, and I've connected that again to my PC to show the content. And I'm measuring first with the microphone here in that distance to the talk box, and then I will increase the distance by connecting actually a second microphone to my XL2. But before I do that, I want to show you the relationship. Let's assume we are measuring 78 dB at position 1. And we have a distance of 0.5 meter from the first microphone to that loudspeaker, which is creating the 78 dB. And then we take the second microphone in 1 meter distance. That would give us an expected level at the second position of 72 dB. Of course, I can also play with that. I could, let's say, enter 2 meter distance, and it would be 66. But here in my setup, I have just 1 meter. So you see 72 is my expected value. So let me switch over to the FX control once again, because I need that talk box for my test. And here on the left-hand side, you see again the XL2 measurement result. First, microphone position number 1. (78 dB) as before, and now I'm gonna disconnect the first microphone, and I connect the second one to the XL2, and I rerun the test. About 72 dB, and that is exactly what we predicted. So you can see the calculation is correct. Well, going back to my slideshow and flipping to the next topic, the noise exposure level. Noise exposure is something that is requested by many standards and laws, which means that an employer, for instance, has to make sure that his employees are not exposed to too high noise doses during their work time, especially when the employees are working in very loud environments. The employer must make sure that the noise dose over the 8 hours work time is not exceeding a certain threshold. So, of course, you could equip all your workers with a noise dosimeter to find out what the reality is. But there is also a better way, a simpler way, and that is you determine the noise exposure level by calculation. How do you do that? Well, of course, you have to know the typical position of the workers and the typical noise level to which they are exposed in the corresponding places. So, for instance, here we have a very loud place, but we know this worker is only 3 hours per day up down here. Maybe then the rest of the time, or 5 hours, he's up here with a more silent work, and then maybe he's even in the office with a very low level noise. So in this way, by knowing the times in which they are present in these locations, you can determine the noise exposure level. And you do that with this formula. So to explain that here, this is the core of that formula, and that is the time period and the noise level. So for each time period, for instance, 3 hours at 80 dB, you would enter these two values. And maybe you remember this sign from your school days. Then you would build the sum of all these periods. So the next period could be 2 hours at 60 dB, whatever, and so on and so forth. For each period, you know where your worker is located with the corresponding level. You calculate this result and you sum it up and enter it into this formula. And that gives you the noise exposure level for 8-hour work time. That is the standardized reference. Just as an example, we have a worker who is 3.5 hours exposed to the 86.7 dB. Then he has 4.5 hours at 72.5 average level. And he has 1 hour break or more silent work with 55.2 dB. Now, if we feed all these levels, these data into that formula, we would end up with an exposure level of 83.3 dB. Which is quite interesting and noticeable. You see that this part here, these 86.7, are apparently the predominant impact or influence on that result. Although the worker was less than half of his time exposed to this level, the 86.7 definitely play a much higher role than these 27.5 or the 55 level. So in other words, take care. The high levels are the most important, the ones with the highest impact. It's the same in a concert. If you have a short time, a very high level, it's getting really difficult to get down the average level to a much lower value because these high levels are really very predominant. This is due to the logarithmic nature of sound. Well, I also want to show you this application in a practical example. For this purpose, I have connected my Flexus generator directly with the XL2 with an electrical connection. And of course, I cannot show you an 8-hour presentation here. I will squeeze that down into 90 seconds, 1.5 minutes. So I will create a sound pressure level of 81 dB for 50 seconds, then 20 seconds, 83 dB, and another 20 seconds at 75 dB. So for that purpose, I have to connect first the Flexus to my XL2, switch off the phantom power, and now I'm going to show you the corresponding screen. Here I have a special project prepared. These are the levels I'm creating Here you see the screen content. Maybe you've noticed down here, I have already prepared a recording time of 1.5 minutes, 1 minute 30 seconds. So I'm gonna start the sequence, which is creating these levels, but first I have to synchronize it, which means I have to start the XL2 synchronously with the sequence on the FX control. So the whole thing has started, and because it is an electrical connection, I can talk to you during that test. There is no interference of my voice to the result. You see here we have 50 seconds duration. Here we see the countdown timer, and during these 50 seconds we have the 81 dB present at the XL2. So we have to wait for another roughly 20 seconds until the system swaps over to the next period. The next period will be 20 seconds with a level of 83 dB, as I have shown you on my little graph. So a few seconds remaining. Second part of the sequence has started. 20 seconds, 83 dB, countdown timer running. So this will be added up to the first part. And in 5 seconds, we're going to see the third and last part of our sequence. And that is another 20 seconds, but now with 75 dB level, as you can see here on the XL2 screen. And as soon as these remaining few seconds have expired, we will see the result. Okay, and that is down here. The LZ EQ is 80.8 dB. This is our noise exposure level. And now I'm going to show you that I would have been able to calculate that as well in advance. And for that purpose, I open this Excel sheet. Here we see 81 dB, 50 seconds, 83, 20 seconds, 75, 20 seconds, and the result is 80.8, the same as you see here on the screen. So if you would play around with that, if you would say, okay, now the first 50 seconds would be 86 dB, for instance, you would immediately see there is a new result, a new outcome of this formula. So in that way, you can easily predict the noise exposure of your workers. Short side note, there is an Excel sheet available for download on our website, which assists you to execute this calculation. You just need to know, of course, the period lengths and the levels that are present at the work positions of your workers. Great. Let us step over to the next slide, and this is the review. Well, in this webinar, I will renounce on summarizing the technical aspects of what I have presented. On this slide, I just actually want to show you the 50 topics that we have covered in the past 9 years. We started 2013 with our series of webinars. The first one was about steeper measurement, and you see all these topics that we have covered up to the current one with the sound level calculations. We had webinars on fundamental topics, what is sound level. We had application-driven webinars. We had even product-oriented webinars. It was always a pleasure for us to have you on board and to get your feedback and to learn from you what is interesting, what you want to know, where we can provide the information you're looking for, and to make your life easier. And of course, we will continue with that, and we're looking forward to your feedback, of course, as well. So that brings me to the end of my presentation. From my side, I want to thank you very much for your attendance. I'm very much looking forward to meeting you at one of our future webinars as well. You will receive an email from us as soon as this is ready. And until then, have a good time, stay healthy. Thank you, and bye-bye.